Hello and welcome everyone. Today we are going to discuss about the wave nature of matter. We'll start with matter waves, or we say matter as wave. After the discovery of particle nature of light, various experiments were conducted after photoelectric effect, Compton effect. Then you have X-rays, diffraction experiments were done. Then suddenly it struck in mind of one French physicist. His name is Prince Louis Victor de Broglie. It's pronounced as de Broglie. This French physicist came with a very brilliant idea that if light can have particle as well as wave character, as nature loves symmetry, why not the particles like electrons, protons, they possess wave character. His thesis in PhD was submitted in the year 1929. Based on this, he found out the wavelength of matter as Planck's constant divided by momentum. P here indicates momentum, and this relation brought him a Nobel Prize in the year 1929. Here momentum, particle like electrons, protons, if they are in motion, then they must have their wavelength as well, and their wavelength and the particle nature and the wave nature, this relation shows the clear picture. Then a particle or a matter must also possess wave character if radiation can possess particle character. According to him, nature loves symmetry, like right then wrong is there, male then female is there, so everything is symmetrical in our nature. When you say good, then the opposite of that bad is there, like that it is symmetrical. So if matter also must surely possess this wave character, that was his saying. He got this relation by using Planck's expression for energy. According to Max Planck, according to Planck's quantum theory, you have energy E is equal to h nu, and according to Einstein, energy is given as mass into speed of light square. If we make this as equation 1 and 2, he integrated these two equations from equation 1 and 2. You have h nu is equal to mc square. H nu frequency is equal to velocity of light or speed of light divided by the wavelength lambda, that is mc square. So lambda is equal to hc divided by mc square. So mc square will come down if you transpose lambda here. One c term, if you cancel it, then you get lambda is equal to h divided by mc. And if a material particle, a matter like an electron or proton, if it travels with the speed of light, it nearly travels equal to the speed of light, then this c can be changed with velocity V. So this one we write as h by momentum. Mass into velocity gives us momentum. If a material particle like electrons travel with velocity v, then this expression we can write as lambda is equal to h divided by mv. In place of c, c will be replaced with v. This wavelength we call it as de Broglie wavelength, or we call it as wavelength of matter as well. We call it as wavelength of matter as well, or matter waves also we say. The wave produced by electrons, protons, particles, we call it as de Broglie wavelength, or we call it as de Broglie waves as well. Now you must be very clear here that matter cannot exhibit both the characteristic simultaneously at the same time. When matter is exhibiting particle character under certain circumstances, it cannot exhibit wave character, and when it is exhibiting wave character, then it cannot exhibit particle character. It will exhibit its dual characteristic under some certain conditions. When it is behaving like wave, at that time we cannot consider matter as particle, and when it is behaving like particle, we cannot consider matter as wave. So it is to be noted. From this expression, lambda is equal to h divided by mv, following observations can be made. From this expression, following observations are made. Let us see one by one. The first observation is that the de Broglie wavelength lambda is inversely proportional to velocity of the material particle. This shows that if the velocity of matter is more, the wavelength is less. As they are inversely proportional, if velocity will become more, then the wavelength will become very, very short or less, and vice versa. That means if the velocity will become less, then the wavelength will become more. So that's the first observation. The second observation is that if v is equal to 0, if the matter is not moving at all, the velocity is 0, then de Broglie's wavelength lambda is equal to undefined. We cannot define any number divided by 0 is undefined. Now in such a case, you cannot observe matter waves. In such a case, we cannot observe matter waves. That means there will be no matter waves if the body is at rest. The body should be in motion, then only we can observe matter waves. De Broglie's wave or matter waves are not electromagnetic in nature because electromagnetic waves are produced by charged particles and the fourth point and the most important point is that the wavelength of a wave associated with a moving particle or matter defines a region of uncertainty within which the whereabouts of the particle are not known. That means when a particle is behaving like a wave, that time you don't know where is the particle, exact position of the particle, and when the particle is behaving, matter is behaving like a particle, then at that time you don't know where the wave is, where the formation of wave is taking place. Out of these two simultaneously, it cannot exhibit both the characteristic one at a time. This statement led Heisenberg in chemistry, you might have studied about the uncertainty principle. Heisenberg's uncertainty principle, you say that the position and momentum of a particle is nearly equal to h cross, and h cross is equal to h, that is your Planck's constant, divided by 2 pi. At the same instant, momentum and position of the particle you cannot measure. You can measure only one at a time. This in chemistry you learn about this, but in physics, from here Heisenberg got the idea about his uncertainty principle. Here, let us solve this question. This is from your textbook, NCERT textbook. So, an electron and a photon each have a wavelength. Both of them, the wavelengths are given the same. Wavelength of electron as well as wavelength of proton or photon is given as 1 nanometer. That is equal to 1 into 10 to the power minus 9 meter. You ask to calculate the momentum of electron to find out, momentum of proton also to find out, the energy of the photon, also to find out. Let us mark as E, and the kinetic energy of electron to find out, kinetic energy also to find out. These are the things given in the question, and some values are also given to you: mass of electron, Planck's constant, speed of light in vacuum. So to start with, we can use de Broglie's equation to find out the momentum of, let us first find same. P, let us see. This is Planck's constant divided by a wavelength of electron. And as the wavelength of electron and photon both are equal, Planck's constant is given to you 6.63 into 10 to the power minus 34 joule second in SI unit. Lambda is given here 1 into 10 to the power minus 9 is also in SI unit. The 6.63 by 1 will get it 6.63 itself into 10 to the power minus 34 plus 9. Subtract it to minus 14 minus 9, 5, and this is 2. And unit of momentum, mass into velocity is momentum. Directly to study in mechanics, mass is kg, and speed or velocity is meter per second. This is the SI unit of momentum. Now the same way, momentum. This is the first one we are doing. Momentum of proton. Also you can find out in the same way. The value will remain the same because wavelengths are equal. You will get the same thing, 6.63 into 10 to the power minus 25 kg meter per second. Then we go to the second one, that is your energy of photon to find out E. The second one, energy of photon to find out E is equal to h nu, Planck's constant into frequency. Again, frequency is equal to speed of light divided by the wavelength. Wavelength, it is for electron we are doing, but wavelengths are both equal for photon as well as electron. This value. H is Planck's constant is 6.63 into 10 to the power minus 34. And the speed of light is 3 into 10 to the power 8 meter per second divided by the wavelength is 1 into 10 to the power minus 9 meter. So it will give you 6.63 into 3. 6.63 into 3, 3 to 9, 1881, 19.89, 19.89 into 10 power, this one minus, if you take it up, will become plus, 8 plus 9 will become 17, minus 34 plus 17 will be minus 17. SI unit of energy is joule. That is, you can find out the energy of photon. That is the second one, energy of photon. And then the third one is kinetic energy to find out. Kinetic energy K. Kinetic energy of electron, K, let me write E, this is equal to momentum squared is for electron divided by 2 times the mass of electron. So now, this one you learned in class 11, the momentum like this. Momentum is equal to root over 2 times the mass into kinetic energy K. From here I did squaring both sides, P squared. Then root you can remove it. After that you can cross multiply and get this relation. Then I will put the values. Ke, or kinetic energy of electron, is equal to momentum square. Momentum we found out here, square it, 6.63 into 10 to the power minus 25 square divided by 2 times the mass of electron. It is 9.1 into 10 to the power minus 31. So we'll calculate it and we'll get the result. So 6.63 square, if you do 9, 18, 8, 1 in hand, 18, 19, 9, 18, 8, 1 in hand, 36, 37, 3 in hand, 36, 39, 3, 9, 7, 8, 9, 16, 6, 1 in hand, 24, 25, 5, 2 in hand, 10, 19, 9, 1 in hand, 10, 13, 3, 1 in hand, 4. After decimal, 4 digit. So I'll write 43.9569 into 10 to the power 25 two times is 50. Divided by these two ones are 2, 2 nines are 18. Into this 10 power, you can lift it up, 10 power 31. Then decimals, if you remove it here, divide by 10,000, 4 zeros, then here it will become 439569 into 10 power minus 50, then plus 31 minus 4, and for this one 0 will come up plus 1 divided by 182. On dividing, you will get the final answer 439569. Dividing by 182, 3 times, 3 2s are 6, 3 8s are 24, 2 in hand, 3 1s 3 4 5. It will become more. 2 it will come then, 2 2s are 4, 16 6, 1 in hand, 2 1s 2 3, 5, 13 6 7, 5. Let's see how many times it will come. 18 2 into 5 times, let us see. 5 2s are 10, it is a 41, 4 in hand, 9. It's bigger. 4 times 182, 4 times 8, 8 4 32, 7 28. 4 times will come, will be 7 28. Then 50 minus 8 is 7, 2. Then we bring down 6. And 2 times 160, let us see, 2 times 2 2s are 4, 2 8s are 16 6, 1 in hand, 2 1s are 2 3. Now 1 time will come, 182. This is 4, 7 minus 8 is 9, then we'll bring down 9, 182, 5 times, 10, 41, 4 in hand, 5 5, 4, 9, so it will be around 5 times, this will be 9, 1, 0, then 9, 3, 0, then here decimal will come, so no need to take the decimal point because we have to write in scientific form, we'll have to bring the decimal here. 2.4 we'll have to write. 2.4 into 10 to the power plus 31 plus 1 is 32, minus 4 is 28, plus 28 minus 50 plus 28, it will give you minus 22, minus 22 into, for bringing this decimal 1, 2, 3 step ahead, you multiply by 10 power 3. So it will become 2.4 into 10 to the power minus 19 joule. This way you can find out the energy, the kinetic energy. Relation between Debris wavelength lambda and temperature T. Let us see. To get the relation between this debris wavelength and temperature, from kinetic theory of matter, of particle, the average kinetic energy of a particle at temperature T Kelvin is, from heat and thermodynamics, is the kinetic theory of gases, that kinetic energy K is equal to 3 by 2. This is Boltzmann's constant K, 3 by 2 K, the temperature T, where K is Boltzmann's constant, and its value is equal to 1.38 into 10 to the power minus 23 joule, J you can write joule per mole per Kelvin. This is the value of Boltzmann's constant. Now we know that momentum P is equal to mass into velocity, and this can be written as root over 2m k as well. It's equal to root over 2m k in terms of kinetic energy, momentum and kinetic energy. Now from the de Broglie's wavelength, lambda we represent as Planck's constant divided by momentum. So lambda is equal to Planck's constant divided by momentum. This value will put it root over 2 times the mass into kinetic energy k. Lambda will become h divided by 2m, root over is there, 2m, k value, kinetic energy value. From kinetic theory of matter we can get it as 3 by 2 kt. This 2 you can cancel it out. Then you can get the relation. Therefore, lambda is equal to Planck's constant h divided by root over 3m k t. This small letter k, your Boltzmann's constant. This is the relation between temperature and de Broglie's wavelength, lambda. Let us do one question and see. See this simple question. Find de Broglie's wavelength of neutron at 127 degrees Celsius. Temperature is given as 127 degrees Celsius. So 127 plus 273. You'll get 400 Kelvin. Then given mass of neutron, mass is given, Boltzmann's constant is given, and Planck's constant is also given. So you can use the relation to find out. We know that de Broglie's wavelength lambda is equal to h divided by root over 3m, Boltzmann's constant into temperature. On putting the value 6.63 into 10 to the power minus 34 divided by root over 3 times the mass. Mass is 1.66 into 10 to the power minus 27 into Boltzmann's constant 1.38 into 10 to the power minus 23 into temperature 400 Kelvin. If you put the values and if you calculate it, you will be getting nearly 1.264 into 10 to the power minus 10 meter. This one can write it as 1.264. 10 to the power minus 10 you can write it as angstrom unit as well. Like this you can calculate it. Here I did not calculate, you multiply these numbers, then 10 power make it, extract the root, and then divide with this number. Try to do and see, try to solve and see. How to find de Broglie's wavelength of an electron. De Broglie's wavelength of an electron. To find out de Broglie's wavelength of an electron, let us consider like this. Let an electron of charge E and mass m be accelerated from rest by an applied potential difference let us say it as V. Then the gain in kinetic energy by the electron, gain in kinetic energy by the electron, you can write it as half of mv square. That will be the gain in kinetic energy by the electron, and we can write it as k also, gain in kinetic energy, and the work done on the electron there is also a measure of energy, that also let us write as k, that is equal to charge into potential V. If you make this as equation 1 and equation 2, since both are energy, one gained by the electron and work done on the electron, both will be equal magnitude wise. So from equation 1 and 2, you will get it half of mv square is equal to E into potential difference V. Here small v is velocity and capital V is the potential difference. So you can write this as V square is equal to 2 EV divided by M, or V is equal to root over 2 EV divided by M. Now this velocity that you got it, if you put it in momentum formula, you can find out the momentum, then you can relate it de Broglie's wavelength. Momentum P is equal to mass into velocity. A mass rated as m into velocity, you can see here it is root over 2 EV divided by m. So if I take this momentum P here, then this mass, if I enter inside the square root, it will become m square into 2 EV divided by m. Now P, the momentum is equal to 1m, you can cancel it out, you will get 2 MeV on de Broglie's wavelength. Lambda is equal to h divided by your momentum P. So h divided by your momentum P is root over 2 m, or we can write 2 EV, and if m is the mass of electron, we can write it as me as well. Now putting the numerical values of Planck's constant h, that is 6.63 into 10 to the power minus 34 joule second. Charge of electron E is equal to 1.6 into 10 to the power minus 19 coulomb. Mass of electron is equal to 9 into 10 to the power minus 31 kg. We put all these values here, then you will get lambda is equal to h, that is 6.63 into 10 to the power minus 34 divided by 2 into 1.6 into 10 to the power minus 19. Mass of electron is 9 into 10 to the power minus 31 into V will remain under square root. So if you calculate this, you will get 12.27 divided by root over V into 10 to the power minus 10 meter. It will come out like this. So de Broglie's wavelength of an electron is given by 12.27 divided by root over potential difference V angstrom unit. This result was actually very useful for understanding Davison and Germer experiment, but that portion is removed from your syllabus, so we'll have to end up here. Let us do one numerical with this and then end up the chapter. Let us solve this question. It's very simple. Only we are doing for remembering this, the de Broglie's wavelength associated with an electron. Just now we found out the relation. We know that de Broglie wavelength of an electron, lambda we used to write it as 12.27 divided by root over V angstrom unit. So lambda is equal to 12.27 divided by root over V is 100, you know. Lambda is equal to 12.27 divided by 10 angstrom unit. This one you can write it as 1.227 angstrom unit. Then if you take the decimal up. So this is the wavelength of an electron associated with X-rays. If you can remember the value while doing chapter 8 electromagnetic wave, you have to remember this value. That's all. Have a nice day and stay tuned with the Educates.